Next speaker, Professor Saito. And actually, Professor Saito and I belong to the same university, Keio University, but Professor Saito belongs to the Department of Physics. I belong to the Department of Applied Chemistry. So we met with each other very often in campus. But this is my first experience to meet you at the academic conference. So please start your lecture.
Thank you very much for the kind introduction, and I also acknowledge Professor Brandon Wu and Sang, who has organized this conference and invited me to come here and give a chance to say something about our work. I think I'm from the physics department, and most of the audience is from the organic chemistry or so, and so I think I'm probably. But this is my name, and this is my co-worker. We are always chatting together in the coffee time, and so this is the product of the coffee time. Coffee time is very effective. So about the chirality, we have already often about the hand and crystals and organic substances and homochirality in life and so on. These introductory part I want to skip because I don't know when I will give a talk. So just in case I have prepared that. And I'm a physicist and a theoretical physicist, so I do no experiment. And so Professor Lahab has warned me once that don't play with the model, but I am playing with what I can do is to play with model. So this is the history of model to understand the homochirality in life, and Frank is, I think, the first proposed the first theory in an open system how to create the homochirality, that is the autocatalysis with neutral antagonism. That I will explain more explicitly later. And then there were soil experiment, but it is done in a closed system, and autocatalysis seems to be of the second order. I only have known Soa's experiment, the first experiment. I came across this experiment just by accident, and then we have thought about a little bit and how the homochirality must be produced by using this one. So that's the main story. And in a while there was an experiment of crystalline chiral crystal growth, and since I have been asked to give a talk on last Friday, I think, and so I will just come back to that part shortly. And my talk is on the fluctuation effect, but first I have to give the study on averaged without fluctuation, and then I want to go to the next stage about the importance of fluctuation. If your questions doesn't kill me before. Okay. So the Young model in an open system. What is it? The apparel substrate is under some chemical reaction changes the material of chiral product R or S, I say, and he has assumed autocatalysis with a rate constant K1, A plus R. The production of R enantiomer is promoted by the presence of already existing R enantiomer. And mutual antagonism means that R and S enantiomer they kill each other, so to say, or they go away from the system. And you can just write the rate equation. The concentration of A times R produces one more R, and the concentration of R and S by linear form the number of R or number of S or concentration of R or S decreases. And you can just draw the flow trajectory in the R and S phase space. And this type of phase space I often use later on. So what I first wanted to look at is what is the fixed point of this flow, this time evolution, and what is found is this racemic fixed point. But this is unstable, as Professor Sakura has already showed. It flows out from this racemic point. It comes in here in this direction, but it flows out. So the chiral order parameter or chirality increases. And how to measure the geometric excess? Why I cannot show the picture here. I should have picture here. I don't know why. Otherwise I have to. So here you see picture. But in a
press once again. Maybe you have this simulation.
Maybe it's in the background or something.
Maybe press once again.
Press once again?
Yes.
No. Here you can already see the graph, but in a slideshow form, I miss it. Here it comes. Okay. So this is the geometric. So I say chiral order parameter, but you usually use geometric excess, and this phi is what Professor Ron has introduced. I don't need any Landau-Ginzburg free energy, but you simply, from the rate equation of R and S, you can just derive the time evolution of phi in this way. It is not complete because R and S are evolving as a function of time. So, but this is a symmetric part in the chiral. Just by changing the enantiomers, and phi represents some asymmetric part. And so, this time evolution of phi is essentially given by this form, and this takes phi as a function, and the phi time derivative as a function of phi takes this form if this part is positive. If mu is positive, and surely R plus S should be positive, the product has to be there. Otherwise, there's no meaning of phi. And then you can see if phi is so the fixed point is phi equal -1, 0, +1. This is racemic state, and this is racemic state. This is homochiral. These two are homochiral states. And the stability, you can see that here, if you start from here, phi time derivative is positive, so that phi is driven to the right. Phi should increase, and then ends up here. Or if you are here, then phi should decrease, and then ends up here. So this is the stable fixed point. These two are stable fixed point. And so, for the Frank model, there is homochirality to this state. And one other things to be noted is that in the time evolution, the mutual antagonism or nonlinearity coefficient mu appears here, but linear autocatalysis is not explicitly shown here. It drops out, but it is important, sure. K1 is implicitly included in the time evolution of R amino acids. Otherwise, every chiral species flow out from the system. So you have to create a chiral species in order to maintain R some positive number, and for that K1 is necessary. But if you use spontaneous production, then this equation changes. That will come later. So Frank has chosen the correct, the simplest, correct.
What about mu? On what it depends?
Mu. Mu is this one.
Yeah.
So the mutual the rate coefficient of mutual antagonism. How fast the system
progress.
With the cross annihilation or the
annihilation.
The annihilation of the
right.
Of
the
the
rate of the
annihilation.
cross annihilation.
We talked about it. There's a cross inhibition exactly that we talked about.
cross inhibition.
Cross inhibition or mutual killing or anything you like. It was the Frank model. So now comes the soy reaction. The soy reaction you have already had a lot, but for me, the name of the substance is too difficult, so I call some achiral, two achiral substrate forms chiral molecule, and which catalyze this reaction system. And in the SoI's paper, we have found, in fact, we have tried to understand it, and we thought second order autocatalysis is sufficient, but it was already published in the SoI's paper. So second order is second order autocatalysis brings this symmetry breaking. Not symmetry breaking, enantiomeric enhancement reaction. In this case, reaction takes place in a closed reactor, not the open system. So let me explain the model. In a closed system, A plus P produce R type of C or S type of C, and which I call R and S. And the possible processes, reaction processes are spontaneous creation, production of from achiral to chiral substances, and in the second order autocatalysis, and of course there is first order catalysis also possible, and that I will include in the formalism. But with this production, I cannot get the homochiral state. So we have wondered how to make the system homochiral, and if the back reaction is included, then it is possible. So that is we have added later. But in the formulation, I include already this part. So the rate equation is the production of R enantiomer with concentration R is proportional, very proportional to the achiral, the concentration of achiral substance, and this is the rate constant, spontaneous and linearly autocatalytic part, and this is secondary non-linearly autocatalytic process. And here I have the decomposition process. The same holds for the S enantiomer, and in a closed system, the total concentration of A and R and S should be kept constant. So we can discuss the flow and trajectories and behaviors in this RS phase space, in this triangular region. Of course, the substance should be positive, limited to C, but since A cannot be negative, A means the concentration of achiral substrate, so it should stop here. And from this simple reaction rate equation, I can derive the time evolution of the national excess order parallel order point like this. So it's a simple back of the envelope calculation, not so difficult. Simply differentiate this and then plug these things in, and then you get this result. So one thing to be noted is that secondary autocatalysis is necessary. Otherwise, you have nothing. If spontaneous process is absent, but the spontaneous process, if there is only a spontaneous process, this K2 vanishes, and phi decreases exponentially. And so the thing is that K1 or lambda doesn't appear here explicitly. That means that the dependence on R and K1 is implicit in this concentration of achiral substance. And the other thing is to be noted is that if spontaneous production is zero, one obtains this then is similar to the Frank model, and that means if K0 is absent, one can reach the homochiral state spontaneously. That is quite natural. If you don't have any spontaneous production of matters, then or the other way around, spontaneous production destroys the chiral enantiomeric excess. So this is this minus coefficient. And so if this coefficient is positive, A and C minus A is positive, as far as this is positive, chiral selection will take place. But the problem of Soy's reaction is a reaction taking place in a closed system. And if there is no back reaction, process proceeds only in one direction. R and S increases in the cost of achiral substrate, so achiral substrate will be consumed. That means A becomes zero in a certain time. That means coefficient becomes zero. So it's a competition. Phi wants to increase, probably if there is K2, the secondary autocatalysis. But the substrate is already consumed up, so you cannot develop any more the enantiomeric excess. And that you can see here in the flow diagram in R and S phase space. Without back reaction, if you start from somewhere here, and if there is only spontaneous production, R and S increases and end up on a line A equals 0, or this diagonal line. In those cases, you can solve the rate equation analytically, or you can obtain the trajectory analytically this way. And this is a line with a slope unity. This is a line projecting out, and this is a curve, hyperbolae. Is it correct? I don't know. So it turns in this direction. But it ends up on a fixed line. And then what is the final value of the EE. And final value of EE depends on the initial value of enantiomer excess, and the amount you have. Initial amount means that you have some finite amount of R enantiomer and S enantiomer, and if you add more so apparel substrate, then the result depends on the number of apparel substrate. And the simplest case is if you have only a linear autocatalysis. Phi 0 is equal to phi infinity. That means it is independent of the initial concentration of apparel substrate. You end up with the same chirality, same enantiomeric excess. And if the spontaneous product, if the process is only spontaneous one, then of course you have no apparel substrate. Then initial and final should be the same. But if you increase the number of initial apparel substrate as the reaction proceeds, the enantiomeric excess decreases because of the spontaneous production of R enantiomer and S enantiomer are the same. Only in the case of second order autocatalysis, you can increase the enantiomeric excess. And so if you start from phi 0 here, and then you run the reaction once, then you end up, for example, here. If you add 4.8 of apparel substrate, 80% of apparel substrate, then you take this apparel substrate as a starting initial material, and then do the same experiment, the same reaction. Then you will increase the chirality. Then you can use that material as a starting subject, and then so on and so forth. By this way, Y has increased his enantiomeric excess. So, but without doing that kind of thing, is there any method, any way to produce to obtain the homochiral state? And for that, A has to be not zero at the end of the time. And for that, A has to be recovered from somewhere. And for that, you need the back reaction. And with the back reaction, the structure of the phase flow changes completely. In the spontaneous case, you have only a racemic fixed point, only a point. In the first order autocatalysis case, you have still a fixed line. And in the case of second order autocatalysis, you have 7 fixed with a certain parameter. You have 7 fixed points, and among them 4 are unstable and 3 are stable. And this is an uninteresting fixed point, that everything has been melted back or gone back to this achiral substrate. And this is the homochiral state with these two are the homochiral states, which is described by the first equation, by this equation. So as for the brief summary of rate equations, without back reaction, final state depends on the initial state. I think that is experimentally sure. And with second order autocatalysis, E is amplified, and that corresponds to the Zoid experiment. And if you include back reaction or recycling, unique final state is attained. And if it is second order autocatalysis, homochirality is possible. But the problem here is that if the initial state is racemic, completely racemic, I is stable, then it is sure by infinity is also 0. So if you start from a chiral condition, you cannot get any chirality. So this is the limit of the rate equation.
But you said this point is unstable, right?
Even if it is unstable, the rate equation cannot say how the later development would be. So that's the reason I have gone to the stochastic process. But before I proceed to the stochastic process, I wanted to shortly review the growth of chiral crystals, which I have already given on Friday, because Professor asked me what you have said. So I wanted to repeat here again, and so this part is clear, and I have summarized Kipping, Pope, and Todipuji, and Wiedemann experiment. But secondary nucleation is rather easy to understand. But the grinding and glass balls by Professor Wiedemann is rather hard to understand. So what's hard? I mean, the usual scenario of crystal growth is the crystal grows step by step by incorporating monomers. That's the usual step of crystal growth. It might be not the reality, but for theoretical analysis, it is the easiest, simplest. And you can simply assume that somewhere you arrive at critical size, and after that you have chiral clusters, and then they develop into chiral crystals. And by adding a grinding effect to this usual scenario, we have done some study, but no chiral selection is observed. So just by incorporating the achiral substrate, you cannot get the chiral crystals, even if you grind the chiral crystals. So so Raha has done some work. Surely I know, but it's difficult for me how to understand his theory. But Wright has given us the very intuitive and very clear, so this hand-waving argument, or clear way of explaining the reason. But for me it was too difficult, so I couldn't find that scenario. So I just have wanted to something more simpler to myself. So I have looked for the minimal model. That is this model. Two monomers form a dimer cluster, and each already has a chirality. So it is not necessarily a real molecule, but some still a chiral cluster, and up to a certain cluster you can have a chirality. Your cluster has a chirality, and I also assume that dimer is critical for nucleation. That means it can sort back to the achiral substrate, but I simply assume that I simply suppress that the trimer and higher polymers, higher clusters will not dissociate, only they dump. But then I have to introduce grinding. So I grind, you can go further down, but the simplest part it might be this point. Tetramer should be grinded and split into two. And so I can, in principle, describe the time variation of monomer concentration, dimer, trimer, tetramer concentrations. And then what I wanted to find out is the fixed point. And in fact, I could have found only a racemic fixed point. So this system. And then this is just the caricature of this more complicated system. Since I cannot only by the incorporation of monomers, I cannot produce the chiral-symmetry breaking, because I can only obtain the linear autocatalysis. So I have to go up a little bit higher level. So I have gone up to hexamer. So R2 is still the chiral unit, and by grinding, hexamer splits into 3 chiral units, dimers, and here is the essential point. Chiral unit is incorporated in the cluster growth. Then this is the equation, a reduced equation for the dimer. But Dr. Waltis explained me how can I derive that. So I can add it another slide. This is the original equation of motion. Dimers are created from 2 monomers, or broken up back into 2 monomers, or a dimer can eat monomer to be a trimer, and trimer eats monomer to be a tetramer. Tetramer eats monomer to be a dimer. Pentamer eats monomer to a hexamer, and hexamer splits up into 3 dimers. And so this is the grinding process. And in addition, I have introduced the incorporation of dimers into the tetramer. So 2 dimers annihilate to produce tetramer. Is it all right, Professor McBride?
Second term of first equation here, lambda. This is a constraint to make the system autoequivalent.
Yes.
Maybe R4 dot, there should be some lambda R2 generate from the R2 generate by question from tetramer. Am I right?
No. Only hexamer. Here in this case, of course you can make anything complicated.
That's why mu and lambda you use different
That's a different parameter. What I'm looking for is the fixed point, whether there is a chiral fixed point, and I want to find out whether it is stable or not. So the fixed point you can obtain by just looking for the stationary position. So this concentration is equal to this equals to that, and this equals to these 2 combination, and this part is equal to this one. So in fact, number of the concentration of hexamer is given as a quadratic form of the dimer. In the original equation, the nonlinear coefficient is negative. That means it is suppressing the enhancement of chirality. It suppresses here. But if you plug this into here, like this, it is more. The coefficient is more in this case, at least. You fabricate more than incorporate. The grinding supplies the material, the chiral material, which to be incorporated in the nonlinear fashion. And this is the equation finally I obtained for the dimer. And since I know that there is a nonlinear autocatalytic process with a positive coefficient, this corresponds to K2, the previous K2 in the chemical reaction. But with this, I am sure that the chiral fixed point is, there is a chiral fixed point, and that is stable. So if you grind R4 to R2, then it produces only a linear instability, and no autocatalysis will be produced. So this is the scenario. This is my scenario. And sorry, I think there should be. There should be one more slide. I think I have had the phase diagram, but I think I have lost it somewhere. I'm sorry. In any case, I
sketch it on the whiteboard.
The phase flow in the R of some means R2 plus R, no, 2 R2, 3 R2, and so on, up to 6 R6. This is the total number of chiral substrate. And if you plot with sigma, then there surely is a limit. They have to be limited, and I think this ends up like somewhere. Yeah, it is not completely homochiral because you have a self-production, spontaneous production. So it cannot be completely homochiral. But with this back reaction too, yeah. So that's it. So this is my scenario. I wanted to reduce the cluster growth to this form because I know that nonlinear autocatalysis produces the chiral symmetry breaking. So I now come back here. So I come and I prepare slideshow. No, from here, where I am. So far, if you have some enantiomeric ingredients from the beginning, then it will be enhanced by the second order autocatalysis. But if you have no chirality from the beginning, no enantiomeric excess, then you cannot obtain the final enantiomeric state. But experiments from chiral initial conditions have been done by many authors, Professor Soai and Shin-Tong and Grigniev. And here I reproduce Professor Soai's experiment. Is there something wrong?
Yeah, it is okay. No, correct.
So there is some probability of numbers of chiral. In some case, it is chiral with a certain percent, and to the S enantiomer, and in another case, it is enantiomeric to the R enantiomers are more abundant, and the probability seems to be double Q. And I wanted to understand this. In order to describe probability, you have to go to the stochastic approach. So I'm sure that the audiences are already tired about my rate equations, and further on, you have to go to the stochastic probability analysis. But so it is necessary. It's not me, the first. Professor Lente in Hungary, I think is the first. Professor Soai has told me this paper, and we have done the similar things. So we need Cuba. So the system is in a box, a closed box of size volume 3, and the state is described by the number of molecules, not the concentration, the number of molecules of chiral substrate and R enantiomer and S enantiomer. And how the probability of this, at the time you can find this state with certain probability, and how this probability evolves as a function of time, that is given by the transition probability. For example, if the transition probability per time of from A to from a chiral substrate molecule, one chiral substrate molecule turns into R enantiomer molecule, then initial condition is this one. There are in A, in R, and S number of molecules. The number of Na molecules decreases by 1. Number of R enantiomer molecule increases by +1. And this rate is proportional naturally to the number of A molecules. And if it is spontaneously, this is the rate, spontaneous rate constant. If there is a number of NR enantiomers as here, then the transition is promoted with a rate kappa 1, that is inversely proportional to the volume. If the system is big, then there is less chance for them to meet. So this represents the probability of meeting. And this is a secondary autocatalytic process. The chance of meeting two enantiomeric molecules with the substrate decreases by the volume square. So this is the rate equation for production. And the rate, transition rate of R decomposition is simply proportional to the number of NR. So with this transition probability, the probability evolves like this. You want to know the probability of that the system exists in a state X. at a certain time t. If the system exists in a little bit earlier time in a state x minus q and make a jump with a jump q, then it comes to this state. So this increases the probability. But if you are already in x state and it jumps to another state, x plus q, with this rate, the probability decreases. So it's just coming in and going out rate equation. And it's almost running out of time. So if there is a decomposition, then you know that you have a unique final state. So by that you can find the final distribution. And final distribution is given in this rather complicated form. This is a combination. This term is governed by the transition rate or production rate. This is the contribution from that. You have to read from zero number of R enantiomer to NR enantiomers, and then for that you have to successively make this kind of NR jumps and with this probability. So this factor comes in, and this is the probability to create NS number of S enantiomers. So in any case, this is the. So if you have only a spontaneous production, then the final probability is Gaussian, centered around the racemic fixed point. That's all right. If you perform a first order, if the system has only a first order catalysis, and then it is a little bit broader, but still a peak at a racemic point, there is something very interesting in the limit of without decomposition, but for that I have no time. If you have a second order of catalysis, you have two possible final states. If you start from a chiral state, then you end up a double peak structure. If you start from a little bit, so this is from the R, there are a little bit more R enantiomers, and then you end up only to this peak. So the symmetry is broken. So you might simply think that if lambda goes to 0 from this, you may think that it is possible that for the lambda equals 0 limit, you may obtain the final probability distribution. But the thing is not so easy. For the spontaneous and first order chiral state, you can reproduce by that method you can reproduce the final state. But for the nonlinear autocatalytic case with this kappa 2 finite, you are. I'm running out. You are out of. I'm out of time. You can project the time evolution to the directed random model. So it is a statistical physics model. We are now coming more and more in the statistical physics. But I'm sorry. So you your system is now in the state with number of NR enantiomers and this number of S enantiomers, and then you change your system wants to change the state randomly, just by increasing the R enantiomers or just by increasing the S enantiomers. So, but that is just random. So it corresponds to a random walk in this NR and S space, and it is directed because it never comes back. I forbid the decomposition, and you can find you can show that the probability to the right is this one. So somehow you can calculate the probability to the right and probability to up. And what I have got is that the final probability depends on the number of initial chiral subs, or the total number of molecules. If the total number of molecules is small, then you have a single peak. If you have an enough amount of molecules, you have a double peak. So what does that mean? If the number of I'm starting from the complete achiral state. Otherwise, you end up in a single peak. So there's no problem. If you start from an achiral probability, achiral state, and if your total number is not large enough, not big enough, then you start. Here I am having a spontaneous production and second order autocatalysis. Otherwise, you cannot start from here. Without spontaneous production of chiral some enantiomers, you stay forever. So you have to have spontaneous production. And if the number of molecules are small, the produced chiral molecules, number of chiral molecules are small, therefore autocatalysis cannot take place. And the system evolution finishes. Therefore, you have only a finite number. But if you have a large amount of molecules, that the achiral autocatalysis comes into play. You have enough amount of molecules that the chiral molecules can perform the autocatalytic process. Then you get the double peak. So this kind of double peak structure with a sufficient number of atoms, initial substrate, this double peak structure might correspond to the SaitoC experiment. That is our explanation. Thank you very much for your attention.
Comments and questions, please.
The little c that you had in the beginning, which was the total number of
Total concentration.
Was that is that actually also varying in this stochastic model with the mass equation?
Total concentration means that the
What is that?
C is
Or is that actually exactly your NC?
yeah.
It's exactly the NC. Is C just NC divided by V?
N divided by N is the total number.
Which is equal, but then you have an NC here, which you actually fix.
No, NC is the critical.
What is C? Yes.
So in order for the double peak structure comes out, you have to have enough amount of initial molecules. And then
So this C is constant then?
pardon?
This C is constant.
This C No. Volume is kept constant here. So if n changes,
I see.
the concentration changes.
And that's, of course, exactly what determines the width, isn't it? Isn't this variation in n then the thing that determines the width in the distribution?
Yeah.
Yeah.
So as if n increases, the peak position doesn't change much, but the width becomes sharper and sharper.
Mm-hmm.
You chose the critical size
Yeah.
and the chiral size to be the same
Yeah.
for simplicity.
Yeah.
Is that right?
Yeah. Only for
But
that
I think
reason.
in a realistic case,
Yeah.
the chiral size may well be smaller than the critical size.
Yeah.
And if that's the case, then you can go to all the way out to the wings. You don't have to stop there. Isn't that right? If the chiral size is smaller than the critical size, then you don't have to worry about this spontaneous generation which is what keeps you from going out to 1.
No.
Isn't that right, or am I wrong about that?
You have, in my case, so important process is the chiral side. Actually, I have to this decomposition, and it can be larger. This is the critical nucleation is. Critical nucleation is R2, but if the critical nucleation is R15, then it comes back, melt back to A's. But in any case, you need to go back to achiral substrate. Otherwise, you cannot change from R to A, R to S. You have to pass through A in between, in crystal growth case.
Oh, yeah, I'm thinking of sodium chloride. Right.
This is the sodium chloride. So R2 cannot need not be necessarily the critical size, but the critical size for nucleation should be critical nucleation size should be larger than the chiral. I think chiral nucleation size. Chiral minimum chiral size. That's my.
That's what I think.
Yeah.
What is it that stops it from going all
Grinding.
the way up?
This is grinding. It feeds back the chiral units. That's what you have also imposed.
What I'm trying to see is that why my system, the way, I mean, that's not the mine, I'm just looking at laws.
Yeah.
But that goes to chiral purity in that system. It doesn't stop at 0.8, which is where your wings are then. Your double.
No, this is not a crystal growth model.
That's the soy one.
This is so I'm going. Sorry. The stochastic thing is for the soy.
So in that case on the left with grinding you do get. You also don't get 100%. No, you also don't get 100%. That was, as you explained, because of the spontaneous generation of monomers. Right?
Yeah. If there is a spontaneous generation.
That seems quite convincing, don't you? And don't you have that?
But if the monomers can't come back to crystals for practical purposes, then you could go to 100%.
If you increase the mass of the system, the peaks get further apart and the peaks really get...
No, it stays here, but the total number increases. That means what it is, E increases. Because the number of S enantiomer remains the same, even though the
mass of the system. If you put more mass, then the water calculus would be more important, so you could try to leak some mass as opposed to
Only one explanation. Adimer has critical size to nucleation.
Yes, yes.
Then adimer is in a supersaturated environment.
Uh-huh.
How can dissolve adimer to reach the alkyl state if it is a supersaturation level? In your model, perhaps there is.
In the model, supersaturation promotes the nucleation.
It is supersaturated.
Yeah.
And it is necessary to reach the alkyl level, only a monomer. But if the solution is supersaturated, how you dissolve this dimer?
Constant grinding.
Cycling.
And the grinding dissolve the dimer into monomer. Is the grinding?
That's why, you know.
No.
The resolution.
The grinding
Perhaps
only-
it is that.
Grinding breaks
The grinding
But
breaks the dimer and do monomers.
It's
in
a
your
6-mer, right?
suggestion. Okay. It's a model.
It's a model, but
It's a model, yes.
But the dimer is not being broken. It's a 6-mer or what?
6-mer is only 6-mer is broken, and
Yes.
this is the usual nucleation level.
Yeah.
Yes.
So even you have a supersaturation for a bulk system, the supersaturation depends on the size of the crystal.
Yes.
See, for an infinite system size plus R over surface tension and something.
Maybe I understand.
So if you have a smaller system, it can melt, and that I assume here.
Maybe I understand. If you grinding hexamer into the dimer, and dimer is equilibrated with the monomer. So once hexamer is grinding to increase the concentration dimer, it equilibrates with the monomer. So monomer's concentration is going to be higher to make the system keeping at the some degree of supersaturation.
That's very physical explanation.
Thank you.
Yeah, for this model,
Yeah.
why do you take the consideration of the solvent? Because if you, let's say, this model, if you grind in without solvent and you grind with solvent, where comes the difference in your model?
Yeah, then in your case, as you have said, then I have to go more realistic model. That is this kind of model. M1 plus 1, and this rate constant. This rate constant is dependent on just like here. This rate constant is depends on the size, and then if you grind, you change this supersaturation. I mean this equilibrium supersaturation is fixed for equilibrium. That means for bulk system. But if you have a smaller system, then the supersaturation changes according to the system size, to the cluster size, and that varies the rate, and see that size dependence. You can change the crystal size as a function of time, and so on and so forth. But all that things complicate and blurs the necessary or important ingredients. So I have skipped all the things.
Only to be clear,
Yeah.
some simple thing. At the final, with the time, you arrive to a situation where the concentration of all species are invariant.
Yeah.
Yes. In the case of the racemic, and in the case of the chiron.
Yes.
The concentrations of all species are invariant.
Yeah. Is it all right?
I don't know, I agree.
Okay.
They are two different equilibria. the racemic and the
Both can be time independent in the final stage.
When you are in the chiral solution, you have invariant concentration. When you are in the racemic solution, you have also invariant concentration.
Yeah.
That's by definition is an equilibrium. They are two different equilibriums, the racemic and the chiral.
In a way, I have the impression you arrived at a merger description of the second order model and the Frank model, because
It's quite similar.
Yeah, it's a merger, because you have, let's say, in addition to Frank, you have added the second order term, but you still have enantiomeric cross annihilation, like in Frank model.
No, I don't have that.
Please go back to the very first reaction.
Okay, I'm sorry to confuse you, but
You had a term where R and S were involved.
yeah,
Micro and mu or something like that.
yeah. That is the Frank model.
And then you came up, as far as I'm...
This one is the Frank model.
Yes.
And mine is this one. You have no cross inhibition.
Okay.
So the model is different.
No, okay, I looked to the last equation. I thought, well, I mean, this is a result of a merger.
Yeah.
So you have second order autocatalysis, first order autocatalysis, and enantiomeric cross inhibition, but you don't need enantiomeric cross inhibition for the second order case.
Yes.
This case you don't need the crossing. If you have crossing, then you just add K2.
You need it for the first order case. You don't need it for the second order case. Okay, so it's due to my stupidity, or let's say that I didn't catch the transition from the Frank model to your model as detailed, because in the equation you write there is no enantiomeric cross inhibition anymore, and so my question is superfluous.
Maybe you can. I mean, you had.
You're right. If the first order of the versus cross inhibition is required, but if it is
If you have second order,
Then you don't need it.
you don't.
Okay.
That's it plays the same
I
role.
thought, I'm sorry for my irritation came from maybe a brief look to my ear, and then perhaps I passed it, that I thought you were right at a merger. The grand unified model where Frank is in and second order, and you can, let's say, make a minimal model out of it by just stripping the terms. The other annihilation will not kill the second order model, right?
No.
Right.
If you add the cross inhibition to the second order, then you lose all your.
No.
Yes.
Just take
You have the right amount
K2 to K2 plus mu.
because there's no second order term which is chiral. If you add the cross inhibition to the second order term, you lose chirality.
No. K2R2A minus mu S. You can simply
You have the same coefficient, K2.
here you get the same coefficient K2, and here you
Because
have
then
the
you
same
have got K2RS and K2RR and K2SS are all the same, and that's not got chirality. That has no chirality. You have every combination of the the same coefficient.
You simply can calculate from this equation the development of phi. Then it is just this.
But no, but if you have K2 RS at the end, if you have K2 in place of mu, K2A in place of mu, so you have the same coefficient.
Sorry,
Take out K2A and put mu.
mu.
So why that?
And this.
Oh, but yeah. No, but wait.
equation.
I mean, the point is, his A,
Well, no, but
his A has a constraint,
yeah. I know it's not physical,
but
but
the total sum is concerned. Otherwise, it's going to infinity, of course.
what I'm saying is that an anti-numeric crossing condition
You
will
want
give you the same results as nonlinear catalysis. Mathematical. It's a symmetry statement.
Yeah, but
Because if you have both cross inhibition and second order catalysis with the right coefficients, that is, it treats all the enantiomers the same, exactly the same, because they've got the same coefficients in the cross term and in the double term, square term. And that has no facility to distinguish.
what is the lambda?
Yes, I mean, no, but not, there's just the opposite sign.
Yes, okay.
But if you reverse the sign, you get nothing. Therefore, having a sign that is physical is exactly identical with the same thing.
But he's got a minus sign.
Yeah, but that must give.
So in this case,
This was proved ages and ages ago in the Russian literature. That you either need cross inhibition or
Enantioselectivity.
yeah, or an antidote.
Yeah, what is the lambda?
And the two are absolutely mathematically conjunct.
What is the
Oh,
lambda?
that's it, yeah, right. He said it.
The lambda there in the equation, what is?
Decomposition.
He actually
The
said that.
competition. Well, that is the inhibition here.
And you
That
can't
is
get-
limited enantioselectivity in the lambda value.
Things, you understand?
That is the limited enantioselectivity in the lambda value.
Everything that-
Without lambda, there is no kind of solution.
Because
Immediately when
this
you
functions coefficient become close to
The
zero.
limited thing is the lambda.
One of his papers had a big change.
Only one question, please. Okay.
Now, only this lambda value, I suppose that is an inhibition. What is the meaning of the lambda?
This is the decomposition. The meaning of lambda. How to achieve lambda? That is.
R2 goes into A plus A.
Origin of calculation. It goes too far, I think. But if the landscape, energy landscape is like this, and this is a spontaneous production, and this is the activated, so
The autocatalytic.
autocatalytic time decreases the
And the lambda is the spontaneous.
lambda is
The backward reaction of the spontaneous.
and so if you have to take into account the lambda of this form, then why don't you take into account of t minus 2 reversal? Because it is easier.
Yeah, he's one of the few.
Then if you include everything, then no chiral symmetric breaking will take place. So if you have a forward and also the reverse,
You mean that with the inhibition of the backward reaction of the spontaneous, of the strike reaction, is enough to break the spontaneous? You mean with the lambda, with
Yeah.
the lambda value, with the spontaneous reaction is enough to break down the spontaneous?
if it is possible, but then why not this process? So
It depends of the values of lambda.
no. So the possible origin of this lambda, I have to go to the open system.
Well, you must have, but not the entrance, but the exit of the system.
Yeah.
Well, that is,
Yeah, you flow in the substrate, a chiral substrate, and you flow out chiral substrate. then you have a flow in of A substrate and flow out with the same rate constant. So the total number is like this. It cannot be, it can be zero. So the total number can be kept constant. But the way. So I have to have the open system.
Is that true? So are you saying in your model of the soil reaction there was no lambda term?
In the soil experiment there's no lambda term.
Uh-huh.
But if you do the soil experiment here with substrate coming in and all the things spilled out, you have some vessel and it flows out from here, which is mixed. Then everything flows out with the same rate. Then you might get this system. But this is similar what, in fact, Professor Soa is doing. You just stop this flow and wait for a while, and then leave it, and then so it is a continuous soil experiment. So if it is possible, continuously running enhancement of inertial model should be possible. That's what we have said in 3 years ago. But the experiment itself is so difficult, and I don't know how to do this kind of experiment. So.
I see. You had this plot there where you showed these two arrows with lambdas downwards. Is that what? Can you show me again? That's maybe what that was. You explained the soil model and the possible reactions there. Yeah, that one. Yeah. So there you did have a lambda?
Yeah, for that you have to, I don't know, at the beginning we don't care about the origin of this package and decomposition. But in order to realize this process, I have come to a dilemma that in a chemical system, in a real closed system, I cannot produce this lambda. So you have to go to the open system. That's what.
I have one comment on this. I have one comment on this model. If the system is isolated, and at first maybe very large amount of static converter here, so chiral asymmetry breaking transition should occur transiently. But if you consider back reaction, make system equilibrium, that slowly go into the equilibrium state. That is racemic. So in Soi's case, the reaction, Manish reaction, I think those reactions, back reaction is very slow. So maybe back reaction and Soi's reaction and Manish reaction, back reaction is very slow. That's why in isolated system, practically isolated system, chiral asymmetry breaking transition, transiently occurs. And if they stop the reaction, they take all kind of material.
That is, and reflection, it is not exactly the same. When you have the exit of the compound, you can compare the open system with the entrance of our with the closed system. And normally in the reactions, synthetic reactions, you are heating,
Heating
the systems, and you have a red constant value, then you stop and you come back to a lower red constant, and then you can separate the product. But in the case of the soil reaction, that is 0 degrees. You stop it, go to 25 degrees, and make the separation. You cannot be the same. But normally in some synthetic reactions, when you stop it, and you have time to separate the product. But in the soil reaction, you are coming from 0 degrees to 25.
Yeah, but in any case, this back reaction is not taken into account. This might be.
Yes, yes.
It depends on.
No, it was all in common about
Yeah.
this, but normally no synthetic reactions could be taken the octave system because then you stop the reaction
And then
and
freeze
then you
it.
separate.
Yeah.
But normally you go to lower rate constant because you are cooling. And in the case of the soil reaction, you are coming from 0 degrees to 25.
Any more questions, comments? You always use ordinary differential equation to see see the behavior of the reaction system. Not only reaction term but also the diffusion terms are included into the system. What will happen?
I have already done it with spatial dependence, but if there is no back reaction, then the reaction just randomly proceeds, and then there are precipitates of R region and S region, and it is completely mixed up. If you only have the decomposition, then you might have some patterns, and I think Brandenburg has also done this kind of direction.
How about
But not a clear pattern formation.
Territories are generated. Territory.
Yeah, territories are generated, and it has to shrink, and the smaller one shrinks, and the bigger one wins, and those
Is it
things.
always the smaller one that shrinks?
Eh?
Is it always the smaller one that shrinks?
It's the
It depends on the
Depends on
structure.
the air.
it shrinks in the direction of curvature.
Exactly.
Sure, sure,
Because
sure.
sometimes the bigger,
Yeah, sure.
and it's quite an important point because you may have a minority
Yes.
handedness
Yes.
that beats out the whole rest of the universe
Yes. Yes. So I
because
had
of the lack of its curvature or structure.
last week I showed an example where you construct an initial enantiometric excess of plus 0.35, and you end up with -1.
But that largely depends on the system size. So
But also the way
it's very difficult to say something very so.
you have a skin depth between them. When you have two domains, you have a skin depth, a transition depth, or is it sharp?
Boundary there, of course.
There's a width. Surely there is a width.
Yeah.
It's a diffusion width.
The design was semi interface.
Yeah.
The design was semi.
Well, it goes from one angle.
Yeah.
Yes.
But I'm not going
It's
to
not
give
your
a talk
fault.
on that. I have also done that, but other people are going to talk on that.
Yes. Any questions? Thank you. Thank you.
Thank you very much.
Lecture today. No more lecture today.